Well, I'd like to welcome everybody to this year's Professor Laureate Awards recognition event. My name is Jacob Roberts. I'm the Interim Dean of the College of Natural Sciences. And I'd like to talk a little bit about the award and then recognize our two award winners that we're going to be celebrating today. So the Professor Laureate is the highest academic title that's awarded by the College of Natural Sciences. It recognizes faculty who are outstanding in research, teaching, mentoring, and outreach. The title is held for 3 years, and it includes an honorarium and 2 years of research funding support. It gives us an opportunity to honor exemplary scholars while providing the college with exceptional role models in these areas. There are 2 faculty members that have received the award this year, Dr. Margaret Cheney from the Department of Mathematics and Dr. Robert Paton from the Department of Chemistry. And while I'll recognize them more fully, let's give them a quick round of applause at the beginning. So I'm going to first present the award to Dr. Margaret Cheney, and then I will present the award to Dr. Robert Paton. And Robert Paton will give a talk and lecture, and then Dr. Cheney will give one in the fall. So Dr. Cheney is the professor and former Albert C. Yates Endowed Chair of the Department of Mathematics. She has extensive research in inverse problems leading to many diverse interdisciplinary projects. So inverse problems are where you have information from an object, you have radiation or something that scatters from it, goes in lots of different directions, and then you have to reconstruct the information from the object from that data that you have that's distributed over a wider range. You can't do this directly. And it turns out originally these problems were limited by hardware, but the forefront of these problems is now in mathematics. And Dr. Cheney has made seminal contributions to work involved in inverse problems in multiple areas. This includes in areas like electrical impedance tomography, where she's written some of the most impactful articles that are often cited in the field. And recently she's moved towards radar imaging and using her mathematical techniques to improve radar imaging in many different applications that range from image processing to optimization to harmonic analysis, all this allowing for more efficient understanding and computation of the data. She has a very high citation rate for all of her papers that are published in leading journals. She's co-written a book titled The Fundamentals of Radar Imaging, and she's contributed to other books as well. This work has both mathematical interest and also real-world impact through applications. And her recognition, or her research work has been recognized by her peers through her being named as a fellow for the Society for Industrial and Applied Mathematics and also the Institute of Physics. In addition to these research contributions and successes, she's recognized as a thoughtful mentor in the department. She's mentored many high-achieving graduate students. They've gone on careers in both academia and industry. She's mentored 36 graduate students, that's 30 previous students and 6 current students. The industries are wide-ranging, including those in engineering, medical device companies, professorships, national labs such as the Air Force Research Lab, technical staff at the MIT Lincoln Lab, and many other activities. She's thoughtful about her mentoring and connecting the work that she does outside of academia to industry and connecting to real-world problems in a careful and thoughtful and disciplined way. She supports her graduate students in the department through a course that's focused on mathematical careers outside academia. We'll hear Dr. Cheney's Professor Laureate lecture in the fall, but I will now ask Dr. Cheney to please join me on the stage to receive her award. All right, they're going to want this, and then we have to actually, I think we need to, we're going to, there we go, yeah, okay, and then we hide that. Okay, then we can use this here, and then, okay, congratulations again, here for the fall, yeah, we're excited. I'll now tell you about the second Professor Laureate Award recipient today, Dr. Robert Paton. Dr. Paton is a professor and recipient of the Marshall-Fixman and Bronco-Ladagna Professorship in the Department of Chemistry. His research expertise is in computational chemistry, which he's received international recognition. His computational chemistry his computational work is focused on transforming synthesis, which has been an empirical field in chemistry, and he's looking for it to become more predictable, more efficient, more sustainable through the application of computational techniques. As an example of some of the work that he's done, he's uncovered mechanisms by which PFAS, they're sometimes called forever chemicals, can be destroyed chemically. These chemicals are pretty robust and will persist in the environment in other ways, and his work has uncovered mechanisms to help destroy these, which is important from both a societal perspective in order to help remove these things from the environment, but also from a fundamental chemistry interest perspective of how can you have techniques which will break down these very solid and stable compounds. This work has been recognized by his peers. He's been named as a Fellow of the American Chemical Society and the Royal Society of Chemistry. He's been a very prolific researcher. Since coming to CSU in 2018, he has over 130 papers published. 10 of those papers have been published in Nature Science since 2020. He's been awarded and granted $4.6 million in funding since arriving at CSU as well. Interest in his work is demonstrated by the fact he's presented more than 80 invited lectures. He's involved in 2 NSF Centers for Chemical Innovation, one of which is in stage 2, represents a $20 million grant, and he's been a founding member of both of those NSF Centers for Chemical Innovation. His research involvement with the community extends to professional service as well. He's chaired and co-chaired many international conferences as one of the ways that he serves his community, and he's going to serve as the 28th chair of an international conference in physical and organic chemistry, which will be hosted here at CSU. So very exciting, both from that role and his involvement, but also the fact that we'll be able to introduce colleagues from around the world to Colorado State University. In addition to his research and his professional service, he's a prolific teacher at many levels in the chemistry curriculum. This goes from introductory organic chemistry classes with large enrollment to specialized graduate courses. He's recently developed 2 new classes in data and computation and chemistry that he's started. In addition to his classroom teaching, he also has extensive and impressive mentorship, 25 graduate students and 14 postdocs, 26 undergraduates and 17 hosted visitors. He's received the CNS Excellence in Graduate Teaching and Mentoring Award in 2025 in recognitions for these contributions. And his students have gone on to faculty positions, both here in the United States and internationally, and played prominent roles in the pharmaceutical industry, along with a wide variety of other activities that they're going on to after they've completed their work here at Colorado State University. Dr. Paton, I'll ask you to please join me on stage so I can recognize you with the award. You can stay up if you want, because we're going to give the talk. I'll get your water. Yeah, okay. So Dr. Paton will now present his Professor Laureate lecture titled, Can a Computer Learn Organic Chemistry? This lecture will be followed by a Q&A and then a reception. So thank you, and take it away.
Okay. All right. Well, thank you, Dean Roberts, for the amazing introduction. Congratulations to my fellow awardee. It's a great pleasure to tell you about some of our research. I'm going to keep it philosophical. I think someone in the audience just asked me, is the answer to this question no? And apparently there is a law of questions in titles, and if the answer was yes, it would be a pretty short talk. Hopefully what you'll see is it's somewhere in the middle, and actually just thinking about successes and failures is more interesting than the answer itself. So before I sort of get on with the show, have a little puzzle. This is for chemists and non-chemists alike, and I've got 2 molecules on the slide. And each of these molecules, they're real. So one on the left is a steroid. The one on the right is caffeine. Hopefully, you're familiar with the one on the right. And what I wanted to ask is, like, in each of these 2 molecules, they have a number of carbon-hydrogen bonds. And we could break any number of these bonds. Some of them are weaker to break than others, and this has real consequences for things like metabolism and how these molecules get sort of processed in the body, and ultimately how they go on to get excreted, or whether they do other things. And I just wanted to show you, in each case, I've got 3 green and gold CH bonds. And maybe for the non-chemists, you can look at the one on the left and try and just kind of guess or reason or intuit which one of those bonds you think is the weakest. And maybe for the expert chemists, I've got a harder one on the right-hand side, caffeine. if you could look at those CH bonds, see if you can sort of predict which one you might think is the weakest. And we'll come back to this later. So really, what I kind of want to get to in this talk is this idea that these molecules kind of look similar, but to expert chemists and maybe even to undergraduate chemists, we can kind of compress our intuition. And really, I want to ask is whether a computer can learn to see what these molecules really are. Can they sort of understand this chemist's intuition and answer the question that I've just asked the audience? So we'll come back to this later. So really, I wanted to unpack the question, whether a computer can learn organic chemistry. I think we have to be honest that, what version of the question we're asking, and really, I can think there are three different kind of parts of this. And so sort of starting at the bottom, you can imagine for a computer to understand chemistry, could it pass an organic exam? Can you, for example, match patterns against textbook problems? And honestly, I was skeptical even sort of 2 or 3 years ago, but increasingly I think that computers and GPT have certainly passed this bar for certain levels of chemistry. And I think if you're up to date with OpenAI, they've just released Rosalind, and it scores about 65% on what they call a frontier graduate level chemistry exam. So that's kind of the base level. I think progress has been pretty good. In the middle, we're sort of ramping up a bit of complexity here. So could you predict an outcome? For example, given some new chemical reactants, could you predict what the right product would be? And this is really what I'm going to talk about today. This is where a lot of current research lives. And then finally, really sort of the top tier problem here, which is the most difficult, is really, can computers explain why? Can they generalize from textbook examples to genuinely novel chemistry? And this is, as I'll show, a hard bar. So I want you to hold this slide in your head. We'll come back to it later. Hopefully, when I've shown you some examples, you have a feel for sort of where we are on each of these kind of 3 benchmarks. So this is how we can judge the progress that we've made here at CSU and more broadly in the field. So I included this because this talk is aimed not just at chemists, also non-chemists as well. And really, I wanted to maybe demystify what it is that chemists do all day. I don't know if my mum is watching at home on Zoom. It's 11 p.m. in the UK, so hello, if you're there. This is what we do. And so I wanted to demonstrate rather than lecture. And so I have a real sort of diagram that's been created by an organic chemist. This is taken from a textbook. And really, this shows the technique known as arrow pushing. And so really what this is designed to show is that the movement of electrons in a chemical reaction, the arrows are not real things. They're sort of a bookkeeping mechanism. Each of the arrows shows where a pair of electron moves from one atom to another. And if you can predict the arrows, you can predict the product of a reaction. This is the output of an expert chemist's intuition. Interestingly, none of this comes from solving an equation. It comes from having seen this pattern or one like it hundreds of times and being able to generalize to different molecules. And so there's a key point here about chemical expertise, which is that it's learned, compressed, and often sort of unspoken. And that's exactly sort of what makes it interesting to ask whether a machine can pick this kind of this knowledge or this sort of intuition up entirely from data. Well, my group is also very much interested in the underlying physical chemistry. And this might look like a completely different universe I'm showing here. On the previous slide, I had sort of a cartoon almost, and now we're looking at an energy diagram. But this is sort of underneath what I showed on the previous slide. So underneath every one of those arrows that's drawn by the organic chemist is quantum mechanics. The shapes of the orbitals, so that's where the electrons live in molecules, the energies of bonds, the height of a barrier that a reactant has to go over to form a product. All of that, in theory, falls out from the Schrödinger equation. In practice, though, no organic chemist, I think, solves the Schrödinger equation in their head. We have intuition, rules of thumb, heuristics, decades, centuries of accumulated lore. Many of it's published, many of it's in unpublished notebooks. The physics is there, but it's been compressed. So there's an interesting sort of gap here between the physics that's lying underneath the way that molecules react and come together, and the heuristics that chemists use on top. And that, I think, is exactly where computers might help us. Either they could do the physics, they could solve the Schrödinger equation and predict the energies of species, or they could help us to learn the heuristics from data, or potentially both. So then this kind of nicely sets up 3 different strategies I wanted to sort of explore for how we might actually compute chemistry. And they sort of broadly map onto different eras, although they're all still active areas of research. So on the left-hand side, really we can think about how computation allows us to study the physics and establish rules, and also that is to encode exactly what we know and solve equations directly. You might sort of could have start from 1960s for this particular era. In the middle, I want to sort of highlight statistical learning. So that is, rather than sort of encode those rules directly, can we train models on examples and let them find their own features or representations of chemistry? Really sort of this century as a sort of serious endeavor. And then finally, sort of an emerging area of chemistry research, and I suspect in many areas of the sciences and beyond, are the idea of foundation models. And that's where we have large models that are trained on huge corpora of data, multimodal systems that are able to process many different inputs. So for the next few minutes, I'm going to take sort of one example from each of these types of computational chemistry. I've got studies from our group, and hopefully show you what we learn from these examples. So first off, we have this idea of encoding chemistry and explicitly establishing rules. Actually, this is a really interesting history and kind of goes back to what you might call expert systems. Really, some of the leaders in organic chemistry came up with rules like LASA, that was E.J. Corey in Harvard, that was predicting retrosynthesis, so how to sort of make a target molecule working backwards, and that used hand-coded rules. Cameo was developed by Bill Jorgensen, similar kind of idea. And the dream at this time was really that if you captured chemical knowledge as logic, you could let the computer do the reasoning. And actually it worked pretty nicely, but it was very brittle. If you stepped outside those hand-encoded rules, everything just collapsed and broke. So what about on the other side of the screen? We have using ab initio quantum chemistry. Particularly in our lab, we use DFT, which is density functional theory, a lot. We're not encoding human knowledge. We're actually trying to encode the physics that underlies chemistry. We effectively solve the Schrödinger equation approximately, but using DFT in particular, we've for the field has used this for 30 years to generate pretty insightful structure and energetic predictions of molecules. Both of these approaches work, but they do have ceilings. On the left-hand side, you have this sort of brittle-based, kind of hard human-encoded rules. And on the right-hand side, physics is kind of expensive. These calculations scale pretty badly as the system sizes grow. They scale polynomially, so they're often impractical for sort of really synthetically useful systems. That sets up this slide, which is a tiny little detour, but I just wanted to kind of make a point here that just compute it is not quite the whole story. It turns out that the accuracy that you would want to get for really interesting and useful predictions in chemistry often boils down to around about 1 kilocalorie per mole. In chemistry, that's often, well, at room temperature, that's a factor of 10. And this can often be the difference between whether a reaction works reasonably at room temperature or not. And so really getting that precision is incredibly challenging. And so DFT, which I mentioned previously, that's kind of a workhorse that the field has used. It gets you close, but things like entropy corrections, this is really statistical mechanics, low frequency vibrations, the assumptions that you kind of use to build the molecular partition function, these all matter. And if you get them wrong, this can mean that you predict the wrong product for a reaction. You're off by more than a kcal. And so one of the tools that our lab developed is called Good Vibes. It's something that we built to apply the corrections that solve some of these issues. We think it's been used in over 1,000 published studies, has, I think, over 500 kind of formal citations, but oftentimes people don't cite software. Please cite software. And I don't want to kind of advertise it too much, but again, the emphasis here is like even the level of getting the numbers right, computational chemistry is still an active research problem. There's still methods being developed every day. The physics is hard. Okay, so that was kind of a slight detour. Let's now jump to this sort of second paradigm or this second area of computational chemistry that I wanted to kind of dwell on a little bit. And so now we're going to flip the strategy. Instead of telling the computer what we know, we're just going to show it many examples and let it figure out the patterns. So to the non-chemists in the room, I have an example here of aspirin. This is the 2D and 3D representations of aspirin. But what's interesting is that a molecule is naturally a graph. So we can say that the atoms are nodes, the bonds are edges. And you have this graph-based representation. Interestingly, you can apply the same machinery that recommends video on YouTube or proteins to AlphaFold. Graph neural networks, which is a technique that we've exploited in the group, took over chemistry around sort of 2017 or so, led in part by DeepMind and Google. So what's interesting about models that leverage the graph-based representation of molecules is that they develop their own description of what matters in a molecule. So we don't tell them that electronegativity is important or pay attention to the carbonyl group. They figure that out. And sometimes they rediscover textbook chemistry. Sometimes they find something we didn't articulate. And as we'll see in a few moments, sometimes they just give complete garbage. And so the key is how to know when we have an uncertain answer. So I have a specific example of our work that uses this kind of approach. We developed a tool called Alphabet. This was a collaboration with NREL, as they were called at the time, National Lab of the Rockies, and the Kim Lab here at CSU. So this is a concrete example where we use a graph-based representation to predict bond association energies. So this is the energy that you need to break apart a bond in a molecule. And this is really important. It tells you where a molecule is most fragile, and it could predict, for example, reactivity, drug metabolism, polymer degradation, and lots of other things. So we care about this property a lot. So we trained on around about 300,000 molecules where we ran pretty high-level quantum chemical calculations to develop sort of reliable corpus of BDE values. And then we trained a model, which is a graph neural network. And once it's trained, it can predict every new bond in a new molecule in under 10 milliseconds, which is around about 6 or 7 orders of magnitude faster than it would take to do the same DFT calculation. So just to be careful, Alphabet doesn't replace quantum chemistry, it amortizes it. So we pay the DFT cost once. We had to do a lot of work up front in those 300,000 calculations. That was during the training of the model. But now chemists everywhere get the answer for free. That's the pattern of successful ML and chemistry that you see again and again. We'll come back to Alphabet in a few slides. It turns out that chemists around the world actually use it. And I think that's a real success for a model like this. Another kind of model that we developed is called Cascade. It was interesting to hear about the work from my co-awardee, where interestingly, what we're trying to do here is take the signal that you get from spectroscopy, that is, from analytical chemistry labs, and figure out what the original molecule was that gave rise to those signals. And so in this particular work, we have a graph neural network model that is able to predict NMR spectra given an organic structure. So we use this framework to try and elucidate chemical structures given an unknown and some associated data. And so for non-chemists, when a synthetic chemist makes a new compound, oftentimes they don't just make one measurement. They often, for example, look at NMR, which is nuclear magnetic resonance. It's the same technology that's used in an MRI in a hospital. They use mass spec, sometimes X-ray crystallography, and kind of stitch the picture together. So it's not really different in spirit maybe from how a doctor might combine symptoms and lab results and imaging to sort of build a picture of what the molecule is. what we found, and what Abhijit, the student in the group who's been working on this project, and now Jake, we found is that the cascade model, we can actually make do with only two pieces of information to determine an organic structure where we have over several 100,000 or several tens of thousands of possible candidates. So, for example, we can take only a spectrum from carbon-13 and a mass and arrive at the most likely candidate given the analytical data that we're presented with. We've also developed metrics to alert when this model is less confident, which is a theme that will come back when I wrap up the talk. What about this kind of third thrust? This is really the most sort of emerging, I think, in chemistry and outside. The current moment, really the same architectures that gave us ChatGPT, turns out you can apply them to chemistry as well. If there are ML people in the audience, transformers trained on reaction data sets, things like patent data, commercial data sets, internal data sets from pharmaceutical companies, they can learn to translate reactants into products as if they were translating English to French. Now for everyone else in the room, for everybody, these models are genuinely impressive at problems within the distribution that they're trained on. They're often less reliable when you ask them about chemistry that's truly new, which of course is often the chemistry that we most want to do. So there's an interesting kind of tension there. So the technology is real, but often the hype is louder than the substance. The example I have on the slide here comes from Meta. So Facebook, all of your favorite company that develops social media apps also is doing chemistry nowadays. This is a huge data set that Meta released, which is being used to train the next generation of foundation models for atomistic simulations in chemistry. So yeah. Okay, so let me come back then to Alphabet. I mentioned that people use it. It's of course one thing to publish a model. It's great though when people actually kind of use these technologies in their research. We in the group deploy our models like Alphabet. We use Hugging Face, which is essentially a platform that allows us to make them openly accessible online. It's public and free. And we also get sort of the query logs, so we can see what people are doing on there. And interestingly, we can see that we have around about 2,500 to 3,000 queries a month currently, even though this work was published now about 6 years ago. So this has really become a mainstay for a broad cross-section of organic chemists interested in bond strengths. And really, this is kind of one of the ways that we think that we are being successful with the models that we're developing. So hopefully we have a user base of chemists who treat this model like a tool, the same way that they treat a piece of glassware. So then let's come to some more interesting questions about when models go right and when models go wrong. I bring up this example. It actually is a pretty textbook reaction that will be familiar to those who've studied organic chemistry. It's an electrophilic aromatic substitution reaction. But this is actually data that's taken from hundreds and hundreds of examples from an industry paper of halogenation of heterocycles. And essentially the name of the game is, can you predict, given a ring, where the bond is formed, which position on the ring is going to react with a halogen? And so we developed a model. We've used our graph neural network-based models, which predicts things like chemical shifts. And interestingly, we can also try and understand how our model is making its predictions. For this particular project, we found that we were able to build a model that 90% of the time is able to successfully predict where these rings react, and also that this maps to a prediction of local electron density. So in other words, the model essentially gets to the point where the more electron-rich sites are predicted to be more reactive, which correlates with what you see experimentally. So we didn't tell the model that this mattered. It learns it from the data. We have several hundreds of examples, I think about 500 plus in this particular case, and it learns them in a form that's interpretable. So we can look inside and see the chemistry, not just the numbers. This is obviously just a small piece of evidence, but hopefully a real one, that we're starting to sort of inch towards this third bar that I had towards the beginning of the talk, this idea of not just predicting outcomes, but also predicting for the right reasons and understanding mechanism. No talk would be complete without some abject failures. And so going back now to alphabet model, it does occasionally and sometimes catastrophically break. I have a couple examples here. These are examples of where our query is really outside of the distribution of our training. And so, for example, when we're trying to predict the OH, or the bond strength of this OH bond, it's very, very sensitive on whether or not there's a hydrogen bond in this starting molecule. And unfortunately, our original model is unaware of this phenomenon, and so it predicts a BDE value that would be consistent with a number that you would see if there wasn't a hydrogen bond, but unfortunately there is, and so we vastly underestimate the BDE for this molecule. Likewise, in the example on the bottom, this is a case where, again, we have a pretty poor prediction, and interestingly what's going on here is that the molecule that you form, the radical that's formed when you break that bond, actually undergoes a second reaction, which is completely unbeknownst to our model. And so again, we have a really nonsense prediction because we're asking it a question that's really outside of any of the examples that it's seen. So this is obviously catastrophic. We can fix it by adding more training data. We also try and use, when we give our responses, we give neighbors in the model. So we basically show queries that are similar to those that you're searching for to provide some context that the predictions are made with. Also, thinking a bit more about sort of LLMs, clearly there are issues with hallucinations. Large language models, particularly guilty of this, and they can write mechanisms with bonds that don't conserve atoms, for example, which may look fluent, but obviously is chemically impossible. Calibration is another real challenge for this area. Even when the prediction is right, the idea of sort of quantifying the uncertainty is often very challenging. And so often a model that says it's 95% sure is probably wrong more than 5% of the time. This is solvable, but ongoing work in our lab and in others. So those of you who are ML experts, these are probably familiar problems outside of chemistry. These are obviously with chemistry specific. I guess for the chemists in the room, these are some examples why you should really treat current models as collaborators and not as sort of divine oracles, hopefully. So putting this all together, if we kind of step back from the specific tools that I've shown and kind of ask, what have we learned in their development and seeing where they work and where they don't, maybe there's a useful reframing here, which is that chemical expertise turns out not to be one thing. It's at least three and many more. But if I were to sort of try and identify three main areas, these are learnable to very different degrees. So we have pattern recognition, which we see as highly learnable. Models can do this comfortably. We have mechanistic reasoning, which is essentially the way that reactants progress towards their products. Partially, we're seeing some progress when the interpretability holds, and that's often in the very simple types of ML models. And then finally, we have sort of genuine novelty and discovery, and really this is the area that's kind of still, I would say, almost or purely human, right? So this is discovering chemistry where we don't have any training data. Models that we've looked at extrapolate pretty poorly in these domains. So maybe the reframing of some of these questions are not really whether machine learning is replacing chemists, but rather what does it tell us about the discipline of chemistry, where it works and where it doesn't. Some parts of our expertise seem to be decompressible from data, and others aren't yet. And those interesting sort of tensions are what the science is actually about. So I wanted to leave you with this picture of where I think this is all going, not just for chemistry, but hopefully for other fields with computational and ML components. We have at the beginning, I think, computers can propose tirelessly, broadly, sometimes wildly. Maybe that's not a good thing. They don't need like 2 cups of coffee to get going like me. But then humans curate, bring judgment, taste, mechanism, maybe cost, price, safety, things that expertise actually contributes. And then the curated outputs we can actually then use to train the next generation of models and maybe view this as a sort of closed loop. This is the model that my group's working under, and hopefully we can build tools that scale beyond what humans can do. But as was mentioned in the intro, we work a lot with synthetic chemists, and they tell us often and frequently when the tools go wrong. So keeps us grounded, and we retrain, we reiterate, and the science emerges from this interface. So finally, let's look at these puzzles that I showed you. I don't know if non-chemists, did anyone get the molecule on the left? Did you predict the bond that was weakest? I think chemists, yeah, nodding. How about the one on the right? That's a much harder problem. You can see that the similarity between those CH bonds much closer. They're all attached to nitrogen atoms in rings, 1 kilocalorie per mole difference. These do have relevance in terms of metabolism. The steroid does indeed get hydroxylated at that position. Caffeine, it turns out, actually gives you 3 different metabolites depending on which enzyme's doing it. So the thermodynamics is there, but there are kinetics as well. But I think the experts may have been able to point to the right bond in 2 seconds, and our model can do it too. These are the values that we get from alphabet. But maybe, unlike some of the experts, it can show you exactly the numerical values. And as was shown, also we can break these predictions down into what features of the molecule led it to those predictions. Is that the same as understanding chemistry? I leave that question open. Let's come back to our scorecard and be honest. Where are we? Well, I think we can pass chemical exams comfortably in many cases, and possibly that's been the case for a few years now. Can we predict the outcome of a reaction? Well, yes, for some classes of reaction, particularly those where we have lots of data. I've shown you our tools. There are other models out there that are real and useful and being deployed. Can we use computation to understand mechanism? Well, we're inching forward. We have obviously some major caveats. We're seeing models whose attention patterns recover real chemistry, but we're not really seeing models that propose mechanisms that a senior chemist would sign off without checking, I think. So that's, I think, where we are. Maybe better than what a skeptic might suggest, but also more limited than the hype suggests. And most importantly, moving forwards. And I will stop there. Thank you for being here today, and happy to answer any questions. Thanks.
So thank you for that talk. Really enjoyed it. We do have time for questions. Start over here.
In your steroid breaking apart example, so as a chemist, what may, you probably didn't do a quick calculation about the numbers. I think they're close enough that what thing would have pointed you to the bottom? Is it having seen a lot of similar molecules and it's always the one on the bottom, or is it the dashed line, or?
Yeah, this is a great question, and if I can teach organic chemistry in 2 minutes. Really, so I would say experts can correct me, but the thermodynamics of this bond-breaking process generates a radical. And so we're kind of thinking about how stable that unpaired electron is that we generate when you break this bond. And in particular, if you put a radical here, it's in so-called conjugation with this double bond and this double bond. So we generate a highly delocalized radical in this product. And so we're not looking at the whole molecule, we're sort of looking just in the vicinity around this bond. What are the neighboring functional groups, and can they talk to one another? And I think that's hopefully how other people might have generated that prediction. This one is obviously much harder because each of these CH bonds, their local environment is pretty similar. They're all next to a nitrogen. They would all have similar kind of stabilization from a nitrogen lone pair, and so it's hard to make that kind of prediction.
Rob, so for predicting or dealing with mechanism, we have Jinx type, all of the IUPAC nomenclature, we know every elementary step. We think we know. Is that being used, or?
Do we know every elementary step?
Well,
okay, so we have an itinerary.
We have those elementary steps. Whether we know all of them, that's a good question. But
yeah, I mean, I guess, but so you get your empirical data, which is reactants go into flask, catalyst goes into flask, product comes out. That per se doesn't tell you which of those elementary steps and mechanisms the reaction is preceded by, right? So I guess you could use those as building blocks to predict what could happen, but you need something on top of that would say this is more likely than this is more likely than this, right?
Yeah, you need other input data. At least you get a list of them, I guess. It's maybe the most probable. But
that could be. That sounds like an interesting way of doing retrosynthesis. Just or apply all possible elementary transformations, but I guess it doesn't tell you what to add.
Yeah. Actually, another quick question. You morphed into my next question. Seems like, where are we with respect to retrosynthetic analysis? Because it seems like Corey started on one of the hardest problems, actually.
Yeah. So just for everybody else, retrosynthetic analysis is the idea you have a final product and you want to work backwards to, if you like, design where you would start to make it from simple chemicals. So you work backwards from a complex molecule towards simple building blocks. There's been some work. It's a problem where it turns out Monte Carlo tree search has been kind of applied by experts to address the real combinatorial explosion that is the challenge computationally. You can also add in things like some physics, some heuristics as well to sort of prune the branches. So I think that's pretty current. Probably still, the challenge is data, which I didn't talk too much about, but all of the reaction data is owned largely by one or two, maybe three companies. And you're not allowed just to download it and start training machine learning models. So you can't download SciFinder, you can't download Reaxys without probably getting the university in huge legal trouble. So often these sort of more practical hurdles that are of limiting things. Yeah.
Thank you for the talk. I've been teaching AI and machine learning for 40 years. But another community I'm involved with has turned to the question of can these large language models construct new combinatorial optimization algorithms? And what we're finding is that you need a rich language to describe those optimization spaces. But once those languages become rich enough, they start creating algorithms that are superior to the ones that humans have been using. So is there a shift that needs to happen here in terms of how we describe these things?
It's an interesting question. I can try and tell you what I know, which is maybe up until a few years ago, probably design of experiments was one of the more popular ways to approach a sort of systematic way to optimize a reaction. That's largely now been superseded by Bayesian optimization in the field of synthetic organic chemistry, at least. That looks to be pretty good at if you can enumerate the reaction space. So if I can tell you the variables and I can tell you sort of what those, how I want to discretize them, like I've got 20 different catalysts, 100 different solvents, I've got a variable temperature scale, it can get you to sort of some global or close to global optimum from those. It's interesting though that if you use LLMs, they often so if you're just starting from no knowledge whatsoever, sometimes people have called this like a cold start problem. Like you literally have no information, so you don't even know the first experiments to do for your Bayesian optimization. The LLMs are pretty good at that because probably, they've read all of the scientific papers in the world ever. Not officially, but unofficially, they probably have. And so those initial, combining LLMs with Bayesian optimization is an interesting approach. There was a Nature paper a couple of years ago that did closed loop reaction optimization of an LLM that was also controlling essentially the experimental chemistry and the analytical chemistry, and that the paper claims outperformed Bayesian optimization purely with the LLM itself. Organic chemistry has a pretty rich language and semantics. Like, it's described in a somewhat kind of formulaic way. So this may well be a domain where the power of LLMs is yet to be unleashed.
Yeah, and a question on over here. Yeah, on your first failure, for lack of a better word, with a hydrogen bond that was or was not there, got me thinking about solvent polarity effects, and just wondering to what extent does solvents affect, confound, or are corrected for in all your modeling?
Oof. There's a famous story. I think it was like Onsager or something. There's like a really famous physical organic chemist who became like obsessed with how to predict reactivity in solution, and kind of went to study it and realized like after 10 years that they should change to the gas phase. Your question is really, it's appropriate and it's a challenge. Actually, homolytic bond association energies of the type here, they're probably the most benign example we could have chosen because we're not generating charged intermediates. So to that extent, we're actually not too concerned. However, certainly OH, NH, SH bonds, they're often the hardest to get right. So yeah, there's a caveat there. The problem is, though, we don't really have many empirical ground truths for those bonds either. So essentially, we rely on our sort of quantum chemistry simulated values as some kind of oracle that we use to train the model. But certainly that's where these predictions will be the weakest. It's also a reason why we didn't do something like pKa prediction or acidity or making essentially charge separated species, just because we know it's currently still a lot harder to handle that. So it's a hard question. It's a hard area. We'll solve it. Give us 20 more years.
So your example of halogenation with the heterocycles, do you have any insight as to the misses? You said roughly 10% were missed out of 500.
Yes. So it's an interesting data set. It's from AstraZeneca, the original work. So it's a European pharma company. They're using different electrophilic halogenating reagents. The failures tend to be, not exclusively, but tend to be for iodination. It's the reaction class where we have the fewest number of examples. So you could make this sort of casual, okay, we just don't have enough data type excuse. Maybe we could make some more interesting hypotheses like switching to different mechanism. Maybe the assumption of electrophilic reactivity is incorrect, could be a radical reaction. Or just kind of in line with other observations that we've made in halogenation chemistry with Professor McNally's lab, there might be a change in the selectivity determining step. It might actually be that, because this is a two-step reaction, you add the halogen on first and then you remove a proton. If that halogenation gets really easy, it's the second step that could actually limit the product that you make. And so if that's the case, which could be for iodination, that would again be a sort of mechanistic reason for the failure. But I think your question is apt because it's often the failures that are the most interesting stories, and those are the ones that prompt us to kind of soul search and try and understand, is the model just limited by data, or is there a fundamental assumption that's kind of amiss?
Along the lines of being limited by data, would it be feasible or practical to take half of the failures, use that for retraining, and then go back and ask, does it work better?
It's a good question. Off the top of my head, I can't remember what kind of split we have for this. And obviously, the data-driven models are sensitive to how you do the splitting, right? Yeah, we can take a look.
So I have a question about how your research, or more broadly AI approaches, are being incorporated into the classroom. How students learn, if at all, and what your opinion is in that regard. Because I think we are in academia more broadly at a point where this is a key aspect. So I just wanted to hear your thoughts about that.
Yeah. As I mentioned, I think initially I was kind of skeptical about even for sort of multiple choice organic exams, how well would sort of the standard GPT type approaches do. And probably 2 or 3 years ago, they would do worse than they would come bottom of the class. I tested some of them. I would say now they're probably more like the middle. And the claim is obviously that they are getting 65% on frontier level chemistry questions. So without doubt, these things exist and they are accessible and being used. So I think we shouldn't dodge them in our classes. We have to acknowledge their existence. I think there are some interesting exercises in, again, catastrophic failures. What do we learn from that? Maybe comparing different outputs. Also, how you ask the questions is interesting as well. What does that teach you? And yeah, that's my kind of current framing. I'm not teaching this semester, so in the fall I will have a chance to kind of put this in action.
Actually, I was thinking a little bit more like, not just how students may want to cheat or not, or use it in an exam and so on, but a little bit more down the road, students that graduate are going to go into a workforce that may actually be expected to know how to use these, or they will have to adapt to use it. And so that, I guess I was trying to, see if in the chemistry department or in your, if there is any thoughts on how this could actually be incorporated in a more organic way to how students then are going to potentially use it. Not just to solve, an exam question, but.
Yeah, I mean, I think these tools are being used. It's certainly in research tasks, like on a day-to-day basis. I've seen some interesting courses on sort of like RAG and things like this that actually teach you to become experts with LLMs. Maybe that's something we have to discuss at the faculty level or even higher. Yeah.
So maybe one more question. Okay.
The only course I dropped as an undergraduate at MIT was organic chemistry.
Oh.
But I stayed away from that. I just worked on complicated three-dimensional magnetic structures. But when graphene was discovered by one of my mentors some years ago, I finally got interested in that. And so my question for you is, and I haven't stayed up with the field, but topological materials, hexagons of carbon and layers, monolayers, bilayers, with extra material to make them into useful systems. Does this stuff work in that area, and has it been used extensively?
Not my specialism, but definitely materials discovery in general is an area that's heavily kind of leveraging computation and AI. Simulations of material properties are commonplace. They kind of have the same bottleneck that I mentioned earlier, which is that those tend to be kind of expensive, and oftentimes those sort of discovery pipelines, they kind of suffer from just it's very slow process to make a material, characterize a material, measure all the associated properties. And so I think some of the effort that's being placed in that field, and probably in drug discovery as well, is in closed loop automation and also sort of the acceleration of some of those analytical bottlenecks that I talked about. So don't know if I fully answered the question, but definitely materials folks are heavily invested in AI, yeah.
Let's thank Dr. Paton for his talk. It was excellent. recognize both of the award winners today again.